Alrighty, folks. So let's go ahead and get started. It looks like, well, we've got basically everybody here. So, like I had said before, we're going to start with questions from the homework, if anybody has any. Dan, when you say 20, do you mean from the problem set, I assume, right? I don't remember how many. I don't remember how far the worksheet went up, but or what the worksheet went to, but okay. Okay. So for this, what I'm going to do is I'm going to start by I would start on the left-hand side because I see an obvious place where I can start using some of my angle sum and difference identities. So I'm just going to think about this as sine x times sine 2x, or sine of x plus 2x. So when I plug that in to the angle sum identity, I just want to double check so I don't write down the wrong thing. I get sine of x cosine 2x plus cosine x sine 2x. And I notice in this problem everything is written in terms of like sine or cosine of u. So I would do this by then doing the double angle formulas. I switch from x's to u, or from u's to x's. I apologize on that, but it's kind of late now to change. So I'm going to go and look at my double angle options for cosine 2x. And I am not positive which one I'm going to want to use, but I'm just going to take a stab. I think that I want this one. There's 3 options for cosine 2x. You could have done the angle sum for cosine of 2x also, if you wanted to. This is a little bit neater, I think, using the double angles, though. Okay.
Oh, real
Yeah.
quick, Mr. Kulik.
Yeah.
On the problems, let's say like sine 15, you would pick the D1, or not D1, sorry, SD1, right?
You're talking about how I went from here to here?
Well, how did you know what identity to use?
Well, because I rewrote 3x as x plus 2x, which is the sine of a sum.
Well, you wrote 3x. Say that again, please.
See how I have sine of 3u here?
Right.
I just wrote it as u plus 2u. I switched from u's to x's accidentally, just out of habit. I didn't mean to do that, but I'm too far along to bother to change it now.
And you wouldn't like... Okay, I think I get it. All right.
Okay. So I think now at this point I'm just going to distribute my sine through. And I'm just multiply this. There's no distributing to do because there's no addition or subtraction in here. And I notice that these guys are like terms, so I can add them together just by adding their coefficients. And then I still have that minus sine cubed there at the end. I think I'm done. Dan, are you happy with that?
Yes, thank you.
Okay, no problem. I think 18 is just, you asked about that one. I think it's almost the identical problem.
Actually, I was looking through it and I think I got it. But
yeah.
maybe not.
Yeah, we can do it real quick. It's not a big deal. But I think it's basically exactly, we'll want to do like exactly the same thing, just we're going to be using the cosum of two angles for cosine first instead of for sine. Oops, should switch the color. That's my gut looking at it, is it's almost the same problem, just sines and cosines are switched. So if I do this, this is going to be cosine x times cosine 2 minus sine x times sine 2x. And then I'm going to use one of my double angle formulas for cosine. I'm not positive which one of the three I'm going to use, but considering that this one worked really well for the previous problem, I'm going to think it's probably a safe bet to try that option for this problem. I'll use my double angle identity for sine. We'll just distribute through here. It's cosine cubed minus cosine x sine squared x. And then distribute, or I don't have to distribute here, so I just have a minus 2 sine squared x cosine x, and those are like terms. So we can just combine them by adding their coefficients, giving us negative 3 sine squared x cosine x, which is what we wanted. So yes, it was almost exactly the same as the other one, just kind of with the other identities. And then Megan, you wanted 19, right?
Yeah.
Okay. So when I look at this one, this one's a little bit trickier. The key here, though, is seeing that I have a 3x over here and an x over here. And I can write both 4x as 3x plus x. And I can write 2x as 3x minus x. So I'm thinking I probably want to work on the left-hand side, because it'll be easy to rewrite this in terms of 3x and 1x. So that's going to be kind of the trick there. Now, having not seen that trick before in terms of like knowing how to break up the 4x and 2x, it's would have been kind of tough to come up with that. But having done that, now we should be able to weasel our way through this now. Go back and just double check my angle sum formula for sine, just so I don't make a boo-boo here. So I have sine 3x cosine plus cosine 3x sine x, and then we have plus sine 3x cosine x minus cosine 3x sine x. And I noticed that these two are opposite signs, so those will just cancel out. And then those two are like terms, so I can just combine those together And we're done so. So again, that was not too bad, but it really relied on kind of deciding to break or how to rewrite sine 4x and sine 2x. If you didn't do that, this would have been rough to get to the end point. You would have gone through a lot of identities and transformations trying to get there, but that would have been the trick there for that one. Okay. Any other takers on the homeworks? Okay. Sounds good. So today we're going to pick up and talk about our last group of identities then. These are the half-angle identities. So let's do a quick little derivation for one of them. The rest of them proceed similarly. So I'm going to start with the power reducing identity. That's kind of where we start with in deriving one of these things. And then I'm going to make a substitution. I'm going to say let x equal u over 2. So then I'll just substitute that in. So there we notice that 2 times u over 2 just reduces down to u. And then we'll just square root both sides. And this is our first identity. So that's our first half-angle identity. I'm going to skip the derivations for the other two because they're quite similar, and I don't think there's any added insight to be gained by doing those. So I'm just going to write them down. Here's the cosine one. And the tangent ones has a couple of different versions. They're all kind of equivalent, but depending on what you're doing, you know, one or the other might be more convenient to work with, but they all kind of do the same thing. So just like the double angle formula for cosine, we had like 3 different versions of it. The same is true here for the half angle formula for tangent, where we have 3 different versions of this. Again, you can use whatever is going to be most convenient to you. The thing that probably needs to be addressed, though, in several of these half-angle identities, we have a plus or minus. Now, the actual answer is not going to be plus or minus that we're looking for. We're going to need to decide whether we want the positive or the negative answer. And the way to do that is we just kind of look at the original. So let's do an example here where we have to do that. So let's say we're going to find the exact value of cosine of 75. And for the sake of argument here, since we're talking about these half-angle identities, I'm going to use my half-angle identities to do this. I recognize that you could use summer differences to do this as well, but so this is I'm gonna use a half angle. So 75 is really the same as 150 over 2. So basically this is just telling me that my u in the formula is 150 degrees. So if I go and I look at my half angle identity for cosine, I have plus or minus square root of 1 plus cosine u over 2. And then if I go to my unit circle, I can look up the cosine of 150, and I think that's root 3 over 2. And we would prefer not to have the fractions inside of fractions here. So let's fix that. So to do that, I'm going to multiply the top and bottom by square root 2 over 2. Now I need the big square root of it because I'm multiplying into another square root. So that 2 in the numerator is going to distribute, and I'm just going to multiply the 1 time in the denominator. Oops, forgot to write my plus or minus there. So that's going to give me 2 plus root 3 over 4. And the square root of 4 is just 2. So I can rewrite it like that. And the last thing now I need to do is determine whether I need the positive or negative answer here. I guess you could have done this first as well. It doesn't matter really when you do this. I'm choosing to do it at the very end. To make this decision, I'm going to go back to the very beginning. Cosine of 75 is cosine in quadrant 1. I know that that has to be a positive value, right? Whatever the value of cosine in quadrant 1 is should be positive. So when I go to the end, I don't want the negative, but rather just the positive. And there we go. Maybe it would have been more convenient to do that sine part in the very beginning. So let's do cotangent of negative 105. So I know this is the same thing as cotangent of negative 210 divided by 2. And I don't have a half angle identity for cotangent, but I do have one for tangent. Just going to use my reciprocal identity to write this as the 1 over the tangent of negative 210 over 2. So here I can see that my u is negative 210. And then I'm going to use one of my double angle identities for tangent, and I'm just going to make it a reciprocal. So the one I'm going to choose to use is this one. So notice that I'm going to write it as a reciprocal. And I'm choosing to do this one because it's going to be potentially the easiest to simplify. I don't have to worry about the plus or minus in this identity. And because I don't have 1 plus in the denominator, if I have to rationalize my denominator, it's going to be relatively easy to do that. Just as a reminder, 210 is this spot here, or negative 210 is here, which is the same as positive 150, right? So just to make our life easier, I can do that. Those two angles are coterminal. And cosine of 150 we've already done. And sine of 150 is a half. And then I'll just multiply the top and bottom by 2 over 2 to get rid of the complex fraction. So when I do that, I get 2 plus root 3 over 1, or just 2 plus root 3. Okay. I guess before we move, any questions on these ones? It's still basically doing the same thing that we did in the previous sections. We're just using some different identities. You know, it should feel quite familiar in that regard. Let's do another example here. So let's say we want to prove the identity. So in this particular problem, again, I'm going to choose to work on the left-hand side because I see the half-angle identity staring me at in the face there. So if I go back and I fill in my half-angle identity for cosine, 2 is going to stay there. And my half-angle identity for cosine was this. Notice since this is x over 2, my identity has x's in it. And because I have cosine of x over 2 squared, when I put in that identity for cosine of x over 2, I also need the squared outside. But that's really convenient, right? Because having that squared on the outside is going to cancel the plus or minus, because I know negative times negative is positive and positive times positive is positive. So regardless of whether it was negative or positive, when we square it, it goes away. And I know the squared also is going to cancel out that square root, which is pretty righteous. And then let's just make that secant 1 over cosine using our reciprocal identity. And now I know that when I multiply that 2, it can cancel that 2 in the denominator. So I can now distribute this 1 over cosine to give me 1 over cosine plus cosine over cosine. And so I just have secant plus 1. which is what we're looking for, which is pretty sweet. Okay. Any questions on that one? Again, it should feel pretty familiar. It's the same kind of ideas that we were using in the last chapter. We just have some new identities that we can work with, but we can still use all the identities that we had in last chapter. We just have some additional pieces that are quite useful. And if you're doing a good job of using those new identities, I think oftentimes these ones are even a little quicker than the previous ones. So our last section in Chapter 6 is titled Proofs and Solving. So these are both ideas that we had looked at in the previous chapter. We just now have access to a whole load of new identities that we might need to use in the course of this chapter. So let's just kind of do some examples, and and then we'll be done with Chapter 6 here. We'll talk about what's going to happen next after that, okay? We'll do two more examples of proofs, and then 2 examples of solvings, and then we'll be done with Chapter 6. Okay. So hopefully at this point you guys would agree with me that let's work on the left-hand side, because I have the double angle going on there. Unfortunately, I don't have a double angle identity for cotangent, so probably my first order of business would rewrite that as 1 over tangent 2x. And then I can use my double angle identity for tangent, but I'm going to write it as its reciprocal. So the double angle identity for tangent is 2 tangent x over 1 minus tangent squared x. I'm going to write that as a reciprocal, though, because I have 1 over tangent 2x and not tangent 2x. But that looks pretty good to me, because I can cancel the 2's. And then if I rewrite this as 2 separate fractions, I have cotangent there, and I can cancel tangents there to minus tangent, and we're done. Well, that wasn't too bad at all, right? Let's do another. Okay. So here, if we take a look, it's probably going to be easiest to work on the left-hand side there, because we see the 4x going on that we can treat a couple of different ways. You could do this as 2 double angle identities, or you could do it as an angle sum. And that's probably what I would think to do. So I would probably do this as cosine 2x plus cosine 2x plus 2x. And then let's see. Well, sine 2x, I have only one option of what I want to do there. This is just going to be 2 sine, goodness gracious, x cosine x. Or really 4 sine squared x squared x. If I look at my answer here, I see that I do have 8 of those, but I don't have, but I'm going to need more than just 8 of those. So we'll have to be careful there. And then this cosine 2x's, I left for a moment because there's 3 options for cosine 2x, and we're going to have to think carefully about what we need there. I think what I'm going to need is 2 different ones, because I need something with both sines and cosines squareds in them, and I need that 1. So if I look back, I want to make sure I get my signs right on this. I'm going to do 2 cosine squared x minus 1, and then 1 minus 2 sine squared x. And I'm doing that because in my final answer, I need a sine squared and a cosine squared multiplied together. So that's, and as well as the 1. So I know I need a 1 in each of these 2. All right, so let's go ahead and FOIL these out and see what I get. So I get 2 cosine squared x minus 2 sine squared x cosine squared x minus 1, and then plus, nope, I'm sorry, minus that's plus, yeah, okay. Minus 1 minus 4 sine squared x cosine squared x. Eek. That got messy. Hold on. I screwed something up there. Let me rewrite that. I got distracted in the middle of my foiling. So I have 2 cosine squared x minus 4 sine squared x cosine squared x minus 1 plus 2 sine squared x. That's better. Okay. So these 2 can combine together. And there's my negative 8 sine squared x cosine squared x. These guys add together to give me 2 from the Pythagorean. And then I still have this minus 1 floating around. So I have 1 minus 8 sine squared x cosine squared x. And at this point, I regret probably not doing the double angle. But, oh well. This worked still. Probably would have been easier to do this as cosine of 2 times 2x and do 2 double angle formulas. But c'est la vie, you know, you live and you learn. Sometimes it's not totally obvious right from the outset which one is going to be the easier way to go. So just as what I was saying is it might have been easier to think about it this way, because then I could have done, I think I would have wanted to do that. Yeah, and that would have been easy to get 2 from there. Yeah, and then we're done. So, oh well. Sometimes your instincts are just off, you know? You think one way is going to be easier than the other. And, you know, sometimes you make a mess out of it or make it harder than it needs to be. Oh, well. Okay. So we're going to solve on the interval from 0 to 2 pi. So we know that to solve these things, first step is usually to get the thing equal to 0. So I'm going to subtract sine x from both sides. And there's no factoring I can do at this point because cosine 2x and sine 2x aren't the same trig function. So what I'm going to want to do is I'm going to want to rewrite cosine 2x so that I only have sines in it. Preferably, that would be the best, which I can do because one of my options for cosine 2x, there's 3 of them, but the one I'm going to want is the one that only has sines in it, that doesn't have any cosines in it. And I'm going to go ahead and just multiply through by a -1 because it'll make the factoring a little bit easier if the leading coefficient isn't 1. And this, to me, looks a lot like a quadratic, right? If I just say a is equal to sine x, that looks a lot like this quadratic, which I could factor or I could solve using the quadratic formula. Either is fine. You'd have to do the long factoring to do this, so let's just do the quadratic formula instead. It might be a little bit easier. So 1 minus a -8 is 9. The square root of 9 is 3. So 1 plus 3 over 2 is 2. And 1 minus 3 over 2 is -1. So I have two answers. I have a equals 2 or a equals -1. But we're not solving for a. Remember that a was equal to sine x. So let's substitute that back in. Oh, shoot. That's a problem, huh? Because it's -b over 2a. Right, was that the only mistake I made there? Oh my goodness. 2a. Jeepers creepers, Kulik. Okay. I looked at this and I'm like, that's not right. And then I couldn't figure out what the heck I was making my mistake on. Great googly moogly. Okay. It's been a long day, kids. All right. So now, if I take the sine inverse of both sides, I go to my unit circle and look for the place where the y-coordinate is positive 1/2. That occurs at pi over 6 and 5 pi over 6. Similarly, I go and look at the places where the y-coordinate is -1. That's at 3 pi over 2. And so these are my 3 answers. Notice what we're able to do here, different than what we did in the last chapter. Notice at no point did I actually have to solve like sine of 2x or cosine of 2x, because before I converted it into a place where I used my inverse, I had just sine x. So I didn't have to do any of that adjusting the things that are coterminal, which is really nice because that was kind of a pain in the butt to do when we had to deal with that in the previous chapter. So let's do one more, and then we'll call it quits for today. So let's say solve let's do all solutions. Well, actually, no, let's do this one. We'll do this one instead. So we're going to solve the interval -4x to -2x. So the first thing I'm going to do is I'm going to get it equal to 0. So I'm going to add 2 cosine squared x to both sides. And again, I'm kind of in a lurch here because there's no way to combine this cosine squared and sine together. So I'm going to go ahead and use my double angle formula for sines. And now I notice that, hey, I have a greatest common factor of 2 cosine there. So let me just kind of factor that out. So I got that. So I can apply my zero product property now and set each of the factors equal to 0. So on the 2 cosine x is equal to 0, I'll divide both sides by 2 and then do the cosine inverse of both sides. And on the unit circle, cosine is equal to 0, whereas where the x coordinate is 0, so that's pi over 2 and 3 pi over 2. But that's not inside the interval that I'm looking on. Remember, the interval I'm solving for is from -4 pi to -2 pi. So I'm just going to find the next small angle smaller to this that's coterminal to it. So I'll just subtract 2 pi from each of these. Still too small, or too big, right? This is bigger than -2 pi, because that's just like -1.5 pi. So I'll just do it again. So that's going to give me -7 pi over 2, and then -5 pi over 2. So that's -3.5 pi, which is in between -4 pi and -2 pi. And that's -2.5 pi. That's in between -4 pi and -2 pi. So those answers are good. Now for this one, what I'm going to do is I'm going to rewrite this as a tangent. So I'm going to subtract sine from both sides, and then divide both sides by cosine. Because sine over cosine is tangent. And then I'll move the -1, divide both sides by -1. So x is equal to tan inverse of -1. So I'm going to go to my unit circle and look for the places where y divided by x is equal to -1. That happens at 3 pi over 4 and at 7 pi over 4. But again, these are too big. They're not in between -4 pi and -2 pi. So I'm just going to keep subtracting 2 pi from them till I get an answer that's inside the interval that I'm looking for. So if I subtract 2 pi here, I get -5 pi over 4. And this one I get -pi over 4. That's 1 1/4 and 1/4. Those are both still too big. So we'll subtract again. So that's going to be -13 pi over 4. So that's 3 1/4. That one's good. And I do that one. That's -9 pi over 4. That's -2 1/4. So that's good. Those are in between -2 pi and -4 pi. So those are my answers. Again, notice that I never had to worry about, like, instead of going 2 pi to find the next coterminal, going like pi or 1/4 pi or 1/3 of a pi or something, because I had to divide after I took the inverse of the cosine function, or the inverse trig function, because in each of these cases, before I took the inverse, I just had an x left inside of my trig function, so I didn't have to worry about that thing that we had to do in the first semester, or the previous chapter. This is still first semester. Okay. Cool. We've now done all of the content for chapter 6. So you can finish the chapter 6 book problems. And you could finish worksheet 1. You should be good to do both of those things. Our next class will just take questions from homework. So I'll do as many of them as you guys want in the time that we have allotted. So you could ask about whatever. We can just do some problems for practice. And so you have that homework assignment. And then today, to finish things off in class, I have in the content library our 6th homework quiz. So if you guys can do that here by the end of the school day, that would be swell. So we're just asking you to find the exact value of something using angle, sum, and difference identities, to find the exact value of something using a power reducing identity, and then to prove an identity. So these should be doable things, all things that you would have done last night in the homework had you tried to do it. You guys should see the homework quiz 6 Dropbox on PowerSchool. So when you're finished, you know, you can do your do this homework quiz on paper or in OneNote. If you do it in OneNote, turn it into a PDF and put it in the PowerSchool Dropbox. If you're doing it on paper, take a picture and put the picture file into the PowerSchool Dropbox. And this will be the last homework quiz for the year. Yeah, I think that should do it for today. Does anybody have any questions about any of this?
Mr. Kulik?
Yeah.
Do we only email you if we want to take the Chapter 6 test?
Correct.